And I'm very pleased to introduce James Young. He's the Senior Consultant, Air Quality and Weather Specialist with RWDI, Consulting Engineers and Scientists. Jim has provided specialized air quality and meteorology services for over 40 years to clients both internationally, in the Canadian private sector, as well as to our federal and provincial governments. His global experience spans issues from climate change and meteorology to acid rain and pollution abatement. He is a past president of the Canadian Meteorology and Oceanographic Society and has served as a member of Ontario's Advisory Committee on Transboundary Science from 2006 to 2009. Jim is a recipient of the Government of Canada Merit Award and Environment Canada Citizen of Excellence, a Citation of Excellence, and a Citation of Appreciation. I'm sure you're an excellent citizen too. He is the author or co-author of over 100 technical papers and presentations. And please join me in welcoming Jim to present Climate Change Already Impacting Infrastructure.
Thank you. That sounds way better than I thought it would. Okay, what I'm going to try to do today is to talk about a number of things. First of all, I have to prove to you that climate is changing, whether you believe it or not. And some do and some don't. And so I'm just going to start in
somewhere else.
So I'm going to look at, is climate changing? Then I'm going to look at what is a building, and I'm sure you all know what a building is, but I'm going to give you my take on that. And I'm going to give you a little introduction to why buildings are important. And again, I'm sure you know all of that as well. And then I'm going to get into some of the meat of how you estimate climate change and what errors, if any, there are in that. And I'm going to then turn that into is there any impact on heritage buildings, and maybe look at some of the opportunities and threats for the heritage community. So the question is climate changing? And the next series of slides are borrowed some from Al Gore's talks. I've added a couple of local things to give you a bit of a flavor for what's going on locally that Al doesn't know about. But let's look at this. So this is the annual global temperature from 1880 to about 2006. And you can see pretty clearly that we're increasing in temperature. Now the point I want to make today is that we're not just looking at a temperature increase when we say climate change, even though a few years ago we made in my opinion, a very bad tactical error when we were trying to sell climate change to the public, because a PR person said, well, climate change, that's not a very sexy term. Can't you get something better? So we said, well, what about global warming? Oh, that's perfect, right? The problem is that it's not just global warming. It's also precipitation. It's also changes, extremes. And none of that is captured by the term global warming, because you can have, in some places, colder situations, in some places, hotter situations. You can have hotter hots, colder colds. You can have wetter wets, you can have drier dries. And that's all a function of climate change, because there's more variability. So, again, here we see the precipitation has been increasing, the number of precipitation has been increasing. You might all remember this one. This is Toronto, August 19th of 2005. 141 millimeters of rain fell in one day, washing out part of Finch Avenue, which is one of the main east-west streets in Toronto. The direct cost to repair this to the city was $47 million. The private insurance costs were above $600 million. And what's interesting is that all this happened in the space of a couple of hours. And every one of these major connections of gas, oil, electricity, not one of them failed, which was a boon in itself, because if one of those had failed, then we'd have had all sorts of other problems. Second one, again in Toronto, 8th of July, 2013. 126 millimeters of rain fell in 2 hours. The insured property losses in the Toronto area reached over $850 million. And this is just because too much rain, the infrastructure couldn't deal with it. How about the Calgary, Alberta flood in June of 2013? In this particular case, 3 rivers, the Elbow, the Highwood, and the Bow, all reached 5 to 10 times their normal flow rate over a space of 1 to 2 days. So damage here, $5 billion. How about Massachusetts? 15th of February 2015, 90.2 inches of snow fell, setting a new 30-day record. And in fact, 1,900 flights in and out of the US were canceled on that particular day. Boston set a new snow record over 7 days of 40 inches. This is unheard of. Nothing in our history tells us that we should expect this. Sao Paulo, Brazil, 16th of October, 2014. In this particular case, we had 140 cities rationing water. It's the worst drought in 80 years, and the amount of rain that fell was about half to a third of the normal rainfall. In fact, over the 9 months, the water reserves were about 16 inches below normal. China. Worst drought in over 63 years. 1 million hectares of crops died. 37.6 million economic losses. The underground water level dropped 15 meters. 240,000 people suffered from water shortages. Again, the scale of this is bigger than anything we've ever seen in the past. Northern California is supported almost directly by reservoirs that are filled up. In January of 2014, over 82% of California experienced extreme drought. This is one of the Northern California reservoirs. The reservoirs were at 50% of their historic levels. Adelaide Hills, Australia, January 2015. This is the hottest autumn on record. There were 32 houses, 125 outbuildings were destroyed, 134 people were injured, 31,000 acres were destroyed. 800 firefighters using 120 fire trucks battled displaced. And this destruction of 3,100 acres happened in 2 days, in 6 days in January. So let's put all this together for the insurance company. This is the growth of insurance claims since 1983 up to 2013. And you can see that it's been, again, growing with time, which insurance companies don't like because then they won't think about raising their rates, which they're going to do, by the way. And let's just put into perspective on this graph. This is $3 billion. The fire that we've just had, or we're having now in Fort McMurray, the estimated losses from that fire alone are $9 billion, 3 times higher than this. So things are changing on a very dramatic scale. A lot of it is probably due to changing climate, and so we have to admit to ourselves that climate is changing. It always has been, but it's changing in a way that we haven't expected and haven't seen for a number of years. So let's look at now buildings. What is a building? Well, it's a facility with complex time-varying interactions with local weather conditions. Notice I bring weather into this all the time. You've got internal loads, people, lights, equipment, appliances, you've got heating and cooling, and all of these things are driven by or react to the weather. Drew Crowley at the University of Strathclyde found that actually the energy consumption declined slightly as we went into the future, according to some of the future scenarios that he looked at. But he found also that the effects were location specific. So here I'm going to introduce a little bit of perhaps things aren't going to be as bad in the future as we think they might be, or perhaps they will be. Why are buildings important? Well, they're the foundation of our social and economic development projects. And this is on the positive side. Public buildings provide infrastructure and operations needed to support democracy and essential services. Housing infrastructure helps fulfill our basic needs for shelter and protection. It generates employment opportunities. It improves public health, supports the development of stable communities. All positive things. But on the negative side, they also are a source of greenhouse gases, which is going to change the climate. So whether an individual house is not going to make a huge difference, but all of the houses that we all live in collectively could. So why should we worry about climate change? The problem is that all of these buildings that we've built were designed around a set of design criteria that are based on the climate as we knew it. So for the last few decades, the extremes were looked at, houses were designed, and safety factors were put in place. If those are now different, then all those safety factors go out the window. The design might have been slightly easier in certain areas or slightly harder. We just don't know. So the problem is that climate change will present a wider range of conditions that push the boundaries of the current design. So the climate impacts on buildings can have far-reaching implications: safety, economic growth, poverty reduction, and development objectives within a municipality or within a community. And so this is why it's important to understand it to the extent we can and to perhaps react to it. So let's look at how climate change works. Climate change the Intergovernmental Panel on Climate Change was set up by the United Nations Environment Program and the World Meteorological Organization in 1988. And they were to be the leading international scientific body to tell the world and all of the decision makers how climate change was going to unfold and what it would do. And so what they've been doing since then is to provide a clear view on the current state of knowledge of climate change. Now, there have been some things that they haven't done very well. There have been implications that they have sort of bent the data a little bit. But by and large, the data supports the fact that climate is changing and things are going to start happening. So by 1990, they started developing future greenhouse gas emission levels. And the reason that they were doing this is that the atmosphere is a big radiative engine. So it reacts to what's in the atmosphere. The more CO2 you put in, the more it controls heat retention. So what they wanted to understand was, as we move forward into the future, how is CO2 in the atmosphere going to change, and therefore how is the heat engine going to change, and how will that unfold in terms of weather? The problem is that emissions are a product of very dynamic systems. You've got demographics, you've got socioeconomics, you've got technology change, and how emissions will actually evolve in the future is still not very well known. So what they did was they developed a range of scenarios to give alternate ideas on how the future might unfold, and these were used as inputs to global climate models to drive them to predict what the future climate would be. So this is the latest series of climate storylines. So what we see here is how the world has unfolded to date and the measurements that have been made. And these four lines here are four indications of what possible futures could be. RPC stands for Representative Concentration Pathway. Why they chose that name, I don't know, but that's what it stands for. So 8.5 represents sort of a high emissions scenario. It assumes that there's going to be a high population, slow income growth, a modest rate of technology change, and energy intensity improvements and a high energy demand. And this curve here will represent the fact that the world will warm up on average by 2 degrees Celsius. The RPC 4.5 is more the stabilization scenario, and that's this curve here where it sort of goes up a little bit and then falls off to about the levels that we are now or have been. So those are the two scenarios that are really looked at. This is the worst case, and this is what we hope for. The stabilization scenario here assumes that the world will increase in temperature by about 1.4 degrees. So what is a climate model and why do we need one? Well, it's really the only way to understand changes that are going to occur to the climate over the long period. What it does is tries to simulate all the processes in the atmosphere and by using mathematical equations. The equations are derived from observations, so they are based in fact and science, physical laws, gravity, energy, momentum, all of that kind of stuff. And they've been used over the last 40 years to project where we should have come. Sometimes they've done a good job, sometimes they haven't. And how have these models evolved? Well, starting in the mid-70s, we included the sun, we included carbon dioxide emissions, and we included rainfall, and not much else. Today, we've got the sun, clouds, in-cloud processes, rain, oceans, recirculation, other pollutants, atmospheric chemistry, the fact that there's an interactive vegetation. So they're much more realistic, the models now, than they were in the mid-70s when they were started. And the way these global climate models are structured is that it breaks the world up into a series of boxes. And this is, for example, one of the ones from the Hadley Center, which is one of the better climate models, in my opinion. And they run two models, one on a grid cell of about 270 by 270 kilometers, 39 kilometers deep in the atmosphere, 5 kilometers deep in the ocean, or 135 by 135, again, the same sort of thing. So you get a much better representation with this model than you do with this one, because what you're doing is averaging everything over that box. So the model divides the world up into boxes, simulates the average value for the weather within each box. The model, for the global climate model, the boxes are 150 to 300 kilometers square each. The problem is that a box that size can't simulate what it matters to us. So when you're trying to simulate a storm that's about a kilometer by a kilometer, it gets washed out in this kind of a model. And the problem is that these models are so complex that it takes hours, days, months to run them unless you have a supercomputer. And if you get anything smaller than about a 50 by 50 kilometer box, you can't basically run the model around the world. So the problem with what we want is about a 1 to 2 kilometer output, and what we're getting is, at best, from the regional climate model, about 50 by 50 kilometer output. And so the approximations that have to be made for how a storm will unfold, what it will do within that 50 kilometer box, and our incomplete understanding of all the physics involved really leads to the types of errors that you get out of these models. But having said that they're uncertain, there's still some reasons to have some confidence. They're based on well-established physical laws, the science underpinning these laws, and how they're represented in models is continually improving. And they have been able to simulate the main features of the current climate and its variability. So, for example, they've simulated the period from 1860 to 2000, and that includes the period when greenhouse gases emissions and concentrations rose from pre-industrial levels to today. And it's done that simulation very well. If we go back this one, you can see here, there's a dotted white line. That's basically the model simulation of the past done by these models. So it's not bad. It's not perfect, but it's not bad. Okay, so I said that we're running the global models on a scale of about 150 to 300 kilometer boxes. Then you have that drive a regional climate model, which runs on a, say, a continent at a scale of about 50 by 50 kilometers, and you have the computer power to do that. But again, you don't need that. What we want is 1 to 2 kilometers. So what I was lucky enough to be involved in was a study for the City of Toronto, or the Greater Toronto Area, where we actually ran on a 1 to 2 kilometer box over the Greater Toronto Hamilton area, covering an area from approximately Guelph to Oshawa on a 1 by 1 kilometer scale. It took 3 months of computer time. That's real computer time. It generated 50 terabytes of data, which you can't even handle files this big. They're just immense, and it takes weeks to transfer the data back and forth. And that was to do an hourly simulation over 2 10-year periods, the period 2000 to 2009 and 2040 to 2049. So the way it worked was, we took the output from the climate model for the period 2040 to 49 and used that as a starting point in a real weather model, because a weather model starts from observations on about that scale, and we used the climate model rather than the observations to drive the future situation. So we simulated all the future hours. Now, a future hour will not match exactly what a future weather is going to be, because how do we know what the driver is going to be a day or two before that? So on average, we thought if we did hourly values and we looked at the statistics, the statistic would probably be about right. So what I'm going to show you now is a little bit of the output from that type of model. But first, let me just show you the importance of grid size. So this was the August 2005 Finch Avenue washout. This is a standard output from a weather model on a 12 by 12 kilometer grid. So this is the forecast we had in advance over 24 hours for the Toronto area. The black circle represents where Finch Avenue is. The dotted circle represents the Pearson International Airport. What was observed at Pearson International Airport over 24 hours was 43 millimeters of rain falling. What was observed near Finch Avenue washout was about 141 millimeters of rain. So quite different. In this case, they were about the same. When we did the same simulation using a 1 by 1 kilometer grid, you can see that the storm was much better defined. You can see that at Pearson Airport we got about 40 millimeters of precipitation, and at Finch Avenue we had a hot spot somewhere between 100, 130 and 140 millimeters of rain over a day. So this just shows you that a 1 by 1 will give you, a simulation will give you a much better answer than a 12 by 12 or a 50 by 50, which comes out of most climate models. But again, the cost on this for this on computer time is huge. So this is just to show you what the simulation actually looked like. This is hour of the day across the bottom. This is the number of millimeters of precipitation that fell in a particular hour. And you can see that nothing happened until about noon, at which point we had 70 millimeters of rainfall. Then there was a bit of a hiatus, and then another 70 millimeters of rainfall fell over another few hours. And what was actually observed was 141 millimeters of rain just north of here, and what the model simulated was approximately 130. So we didn't get it quite right, but much closer than the 43 at the airport. And then this is just to show you over a couple of hours what happened. This is Finch Avenue here. This is a creek that was coming into it below. And as you can see, the water level here was about 15 to 20 feet above normal because of 70 millimeters of rainfall in 3 hours. And you can see it did a nice job on taking out the road. And this basically just points out the folly of not acting responsibly now. So for example, the people who were responsible for cleaning out the culverts decided, oh, it can wait another 3 months. And there was a log covering part of the entrance to the culvert. So when this high water level came, it may not have done anything, but it pushed more of the water around the culvert than through it, and that's why it took the road up. So you're talking about $650 million of damages and insurance claims just for the lack of somebody going out one time to a site to remove a log. Okay, so what did the model for the Toronto on the 1 by 1 kilometer scale show us? What I'm pointing out here are what are called the IDF curves. These are the curves, they're intensity, duration, frequency curves. These are the things that are used to design sewers and size them properly so they'll handle the volume of water that will come down. So this is the maximum precipitation in millimeters over a 24-hour period. And here's the old data from the 1940 to 2003. And you can see, now remember what fell there was about 141 millimeters of rain. Well over the 100-year storm, so that was a 1 in a 100-year storm at least. So when we simulated the same situation for the period 2000-2009, we found only 81, which again is about the same as it is here, but not quite as good a match because this is over a much longer period. And then when we go to period 2040 to 2049, again, we're looking at double the current design. So if you've got a piece of infrastructure designed now with the old curves for a 1 in a 100-year storm, it's not going to last. So this just points out the types of things that you need to worry about when you're looking at building any kind of infrastructure. This is the difference in extreme daily precipitation between the two 10-year periods. And you can see that they're all on the positive side, they're all increases, except for December. And ranging all the way from about a 10% increase here to about a 200% increase in July. And this is in total daily extreme precipitation. Similarly, looking at snowfall, sorry all you skiers, not going to be much use for you in the future in 2040, 2049, maybe. What the model shows is that between about a 90 and 10-15% decrease in all the snow months. That's good for some people, bad for others.
Yes. I'm understanding you're saying this is an extreme snowfall, so this is not the average for a month or whatever. It's
No, this is extreme.
How much falls at sort of one event.
Right. Yep.
Do you have information coming up on the
Averages?
averages?
No, I don't, but I can get it for you. The problem is that everything has been designed on averages, and the problem is the infrastructure responds to extremes. So I'm just giving you sort of a flavor for how the extremes are going to change, and then I'm going to flip over to talk about heritage buildings.
No, I was just curious as to if it was.
Yeah, you have my card.
Well, is there a significant change also affected as to, how much snow would you end up piled up?
Excuse me, if we could just hold the questions till the end, and then perhaps you could exchange
Yeah.
cards and.
Yeah, yes, there is.
that.
We can talk.
Yeah.
Thank you.
Okay.
Okay, so this is about a 50 by 50 kilometer square over the city of Toronto. And this I put this up just to show you how the snowfall, the total snowfall over the winter season would drop by the 2040s. So these are all negative numbers, they're all going down. And you can see that they range from about a minus 60% here to about a minus 140 or 160% down around the lake. Now, again, whether this is realistic or not remains to be seen, but the point to make here is that with the modeling techniques, the fine scale modeling techniques that we have now, you can actually get these distributions which make designing infrastructure, or the decisions you make about designing infrastructure, much more easy, rather than getting one point, which would be the average of all of this out of a climate model. Okay, this is again looking at Pearson Airport. This is the change by month in rainfall and snowfall and total precipitation. And basically what it shows is that in the winter time we're going to get less snow here and here and more rain. Now, that doesn't mean that in every year it's going to be like that, but on average over a 10-year period, that's what the change is going to be like. So in summary, for Toronto's climate future, you're going to have in the future only 9 heavy rain days per year, as opposed to 19 now. But the problem is that those 9 will carry a lot more precipitation each one. So you're going to get more powerful storms with more precipitation, but fewer of them. So you're going to get bigger events, about the same amount of rain probably will fall overall. You're going to get heat waves, almost 4 times as many heat waves. You're going to get 3 times larger number of hot days, greater than 30 degrees, and the daily temperature maximum will be up from 37 to 44 degrees. So quite a substantial change projected for Toronto if you look at extremes. Now, how does that relate to the rest of Southern Ontario? Well, I don't have obviously the same types of things for Southern Ontario, but what I have is a more general output of an annual warming of about 2 to 4 degrees, and the change in Toronto, by the way, was about 6 degrees. The increased annual precipitation of somewhere between 2 and 13%, and a rainfall increase and a snowfall decrease maybe. A recent paper has just come out that suggests that actually the snow or the lake effect snow may actually increase because the lake is going to be not ice covered, and therefore more moisture will be available to be picked up, and therefore you may have more lake effect snow in the future rather than less snow. So you may have less snow overall, but more lake effect snow. So again, it's very hard to make a decision. So the only conclusion you can really draw from these models is that you're going to have more variability. You're going to have hotter hots, colder colds, wetter wets, more rain, less rain, more snow, less snow, and it'll all be location dependent. So, increased frequency of and severity of extreme weather events, heat waves, drought, extreme precipitation, and increased lake evaporation. The projections are that Lake Erie, for example, may be lower by about 1 meter by the 21st century. So, by late in the 21st century. So, again, that has a huge impact on shipping and infrastructure along the shoreline. So you're going to get a decline in the extent of ice and snow cover. Winter storms will be, the total number of them will decrease. The intensity of each one will increase. Wind speeds during intensive events may increase the impact on infrastructure. For example, a 25% increase in wind speed equals about a 650% increase in the damage to a building, just because of the wind pressures. And we'll have increased wave heights and sea effects, and storm tracks that are now down in the US will move up into here, so we may get more tornadoes. Okay, let's flip over to what does this mean to heritage, which is a wider here. And which heritage is going to be, or heritage buildings or heritage infrastructure is going to be at risk? In my opinion, all of these. You've got buildings, you've got bridges, you've got culverts, you have individual houses. I'm going to look at it from a couple of different ways. I'm going to look at it from the point of view of opportunities and threats, and then I'm also going to look at it from the point of view of looking at infrastructure or operations. So let's look at increasing temperature first of all. You can have, basically an opportunity is that because it's going to get warmer, the deterioration rate on a lot of the buildings on basic structure will decrease. So that's an opportunity. You'll have less improvements to make or less changes to make. And you also may have an argument to make to a funding agency to get more money to improve the efficiency of heritage buildings. On the threat side, you've got increased energy use due to heat waves because you have to cool these buildings. You may get deterioration of the surfaces of buildings because of the sun beating down on them. You may have insect infestation because it will be a nicer regime for insects. You're going to have more UV damage on the paints and the roofs. And basically you're going to have probably a reduced service life of some of the components and systems that are in the buildings now. So looking at it again from the infrastructure side, from the infrastructure side, you're going to have increased cooling demand. You're going to have premature deterioration of the structure and the equipment. You're going to have changes in the dimension and shape of the building materials and equipment because you're going to have more cracking and fissuring, and you may have insect infestations. From an operational side, you're going to have heat stress, health problems, and reduced productivity to the workers in buildings, not just heritage buildings, but all buildings. You've got damage to sensitive systems that support the operations, like the electrical system. You could have impacts on the use of the building equipment, like the heating and cooling and waste and water systems. And you may have disruptions in the construction and maintenance activities and supply chains because of the storms that will stop trucks, cars arriving. From the precipitation side, the opportunity is that you may have, in some locations, less seepage and flooding, less cost for water for the gardens because you'll have more water from the sky. You'll have maybe less snow load. You'll have less cracking due to low relative humidity levels. And again, you'll be able to argue for funding to improve drainage because climate change is happening and therefore we need money to support that. And you're going to have probably the opportunities to improve flood risk protection. On the threat side, again, you'll see a lot of these are parallel here. You'll have more seepage and flooding depending on the way it goes and the location. You could have more corrosion of materials. You could have more washouts. You could have compromised foundations because you have either too much or too little water. You have more fungi and mold growing. And with more wet, dry, freeze-thaw cycles, you could have more damage. Flipping that over to the opportunities and threats side. Oops. You may have an increased number of visitors that want access to the heritage sites. With less winter snowpack, it means you're going to have lower spring runoff. So that's both of those are opportunities. On the threat side, you have extended dry periods during the summer, more frequency and severity of drought. That may reduce the irrigation water, therefore you need more conservation. The extra heat may increase the fire hazard. You may have the number of extreme rainfalls may have major impacts on heritage structures, either undermining them or overpowering the systems that were designed to do this. Again, looking at precipitation change from the infrastructure operations point of view, increased precipitation will maybe lead to more seepage and flooding in interiors, physical changes to the building materials and finishes, washout of poorly constructed structures. If you have increased precipitation in a location, you've got increased soil cracking and subsidence in areas where you have clay soils and reduced soil moisture. You have damage to building foundation and facade from the ground movement and subsidence. On the operations side, you have impacts on worker health, safety, and well-being, potentially caused by fungi and mold. You've got disruptions in the maintenance, repair, and supply chains due to flooding. You could have inadequately functioning and or stressed water and waste systems. So there are a number of things that will happen. So from the precipitation side, I want to just look in a bit more detail at this because precipitation is particularly important to heritage buildings. And what I want to look at particularly is snow loading. I'm not going to really look at ice accumulation because that really depends on too many things. But snow load is something we can do something about. So, increased extreme weather. I'm saying less structural damage to heritage buildings, but that may not be an opportunity. Some of the heritage buildings appear to be better built than some of the modern ones because they were over-designed a bit because we didn't really know what we were doing when they were built. Now we've learned a lot more and we're cutting corners and we're trying to say, well, it only has to be this strong. But some of the older buildings are designed to last a lot better. You've got probably the same upkeep costs because of extreme weather, because you've been through extreme weather in the past, the buildings have lasted, they haven't fallen down. And again, more opportunity to argue for funding to adapt the building to survive the extreme events. On the threat side to increased extreme weather, you've got potentially structural damage due to high winds, and I'll tell you a little story about that in a minute. You've got exterior surfaces that will degrade faster. You've got maybe safety concerns due to the violence of the storms. You could lose windows. You can have more impact within floodplains, and you can have saturation of masonry walls. Looking at this again from the infrastructure or operations side, structural damage due to changes in intense weather patterns on the infrastructure, reduced durability of exterior surfaces due to erosion and weathering, and accelerated deterioration of building shells due to the increase in particulate matter and smoke. Now, the increase in particulate matter and smoke comes from the fact that you're coming out of a hotter situation or a colder situation, and you're generating more electricity, which means you're putting more pollutants into the air, therefore you're increasing the particulate and pollutant load. On the operations side, you can have disruptions in operational activities and supply chains. You can have increased safety hazards and physical damage to the service workers. You can have increased disturbance to the operational support services like the stormwater and electricity system. So what I want to do now is just show you a little bit about what we are already doing that is just a function of our lifestyle. So this is, each one of these yellow dots represents a plane. And I'm going to just play this, and what it does is it plays, oh, no, it didn't do it. It plays a 24-hour period. You can see here the nighttime shadow. And this is just what we are doing, emissions from planes worldwide. So you can see we have quite a volume of traffic in the daytime. It falls off a bit at night. Again. But each one of these is putting pollutants into the air. Those pollutants are affecting the climate. And that's just one part of what we do. I haven't even looked at traffic or anything else, or factories, or what we want to do in our houses, or cooking. So it just gives you a sort of a perspective of that you probably haven't had before of what we're doing to ourselves. Okay, so there are a couple of other things here. This is a picture down here of the end result of the tornado that went through Goddard. And it showed us a couple of things. There was a house in downtown Goddard that was very similar to a house that was just outside of the path of the storm. The one in downtown Goddard had been renovated, the windows had been improved, had been tightened up. And because the windows had been tightened up, you had basically an enclosed pressure vessel. And as the storm pressure center went across the building, the building basically imploded because there was more pressure inside the building than there was outside, and it became a pile of rubble. The woman who owned the house on the outskirts of town had the same, almost the same pressure differential going across her house, but she remembered that in her youth, her father had said, if there's a storm coming, just open the windows. So she opened the windows and hid in the basement, and she lost 3 or 4 tiles on her roof, and that was it. Okay? So the modernization things that we do, we have to be careful about. Okay? So you put in tight, airtight windows, you're creating, in this situation, a bomb. You know, and I'm going to show you something else that we can do too, that to old houses that again may be the wrong thing to do, or may not. So what I'm saying, the point I'm making here is that houses, some of the older houses may stand up better than the modern ones, just because they're over-designed a bit. There are other threats that we haven't even talked about, like salt splash that we use on our roads. They can destroy electrical systems. You're going to have increased insurance claims, which means your insurance rates are going to go up. And when you're trying to do repairs, you can have hazardous waste streams like lead pipes or asbestos insulation. So again, all of these things not directly related to climate change, but related to the fact that we live in a society and we have all these things in our old houses, and we try to do things about it. So again, this is just to show you how uncertain our infrastructure is. So this was August of 2003, and I'm sure most of you remember it. There should be, this little part here should actually be all lit up, but this was when the electrical system failed in Eastern North America, and in the middle of the day, and was out for about 24 hours because it overloaded, somebody did something stupid, and the system failed because it wasn't designed to handle what they were trying to do to it. So these are the types of things that, again, challenge us and challenge our infrastructure. So let's look at a little bit more about wind impacts on buildings. And the reason I'm going to do this is because there are things that are important. So again, you may have remembered the Tacoma Narrows Bridge that had hit the exact right frequency for the bridge, and it basically destroyed itself just because the wind was blowing at the right frequency. We've all experienced this. The other thing is today a lot of buildings are built with cladding on the outside, and the cladding is designed for a certain pressure level. If the pressure level gets higher than that, it'll pop the cladding off. So again, you have to be careful how you design a building, and it's important to get it right. Older infrastructure may need to be replaced or upgraded due to the increased risk of failure. Buildings can be buildings can be undermined. The drainage systems may be stressed. The bridge supports may be damaged by flooding. And there's more cost for flood prevention. So there's more demand for summer air conditioning. There will be more insurance claims for flooded basements. You're going to have increased repair costs, and reserve fund contingencies are going to be used up within municipalities. And there is increased liability as a result of premature aging or deterioration. The future can also bring us safety problems. Dust pollution, because it's hotter and drier, medical impacts due to flooding, heat waves, severe storms, snow loads. So let's look at snow loads on structures. And then this is important really for heritage buildings. So you have an increased severity of winter storms coming. That means that the building code that we're now using, a 1 in 50-year storm may become a 1 in 25 or 1 in 30-year storm. So if you have slight changes in the temperature or the weather patterns, you can modify dramatically the local snow loads, the snow density, and the freezing rain accumulations. And so the buildings will experience new and different weather scenarios and potentially increased ice and snow hazards. So this one is just to show you, the two graphs here are, we have an increased insulation due to snow loads. and this is the best case orientation, and this is the worst case orientation. So what you see here is the peak load in blue and the uniform load in white. And this is the changing from, the change in snow loads when you go to R12, from R12 to R30. And this is when you go from R12 to R30, again, for the peak, for the worst case condition and the best case condition. So you might think increasing roof insulation is a good thing because you're trying to reduce heat loss, trying to reduce your operating costs for a heritage building. But what it may do is increase the snow loads and put the whole building at risk because you're putting too much snow load on the roof. Now this may not happen either, okay? But there is a real potential in some locations with some heritage buildings that this could happen. So it's important really to understand what kind of future is coming for each of your locations and what you should or should not do about it. So, practical things. You put insulation inside a roof. What that does is it makes it a colder roof. So the heat escaping from the roof doesn't melt the snow, so the snow stays there. So the snowpack gets bigger and thicker. And going to an R30 roof and increase your design loads by 7%. Going to an R40 roof, you can have an increase in load of about 10%. So as long as the roof is designed to withstand that, everything is fine. But for older buildings, in the pre-60s, it might be best to avoid insulating. Even though you're going to save money, you have to take into consideration the fact that snow loads could increase. So you either have to do a bit more design work, a bit more thinking ahead of time, or just don't do it. Tourism. There may be more demand in the future for visits to heritage sites because it's going to be nice and warm and people want to get out. So you have more income for visitors, you're going to have less winter recreation, so they're going to be looking to do something else. You're going to have more summer recreation, so that might take them away. But there might be more insects and bugs, so that might keep them away too. So again, it's always a range of things pulling you one way and the other. So what should we do? Well, I think we have to accept the fact that our climate is changing. We have to develop some certainty about the future weather in our particular area. And you can do this, as I showed you, by running a fine scale model driven by a climate change model. And it gives you a lot of information about what will actually happen in terms of snow load, either average or extreme, in various areas across your area of interest. And you could actually plot on there your heritage infrastructure to find out what the heritage infrastructure is going to be exposed to. You can use this data to inform your current decisions about what you will do or what you will not do about a historic site. And you could even go further and develop what's known as an infrastructure risk model, which basically takes a location and says, okay, what is this site connected to? Is it near a river? Where does the electrical system come from? What will happen if I have extreme weather in the future?
Go ahead.
Where will it impact?
So you know where I would find Aaron?
And so you can actually build an infrastructure model that will allow you to look at the infrastructure at risk and do what if scenarios. What if the snow load goes up? Will that impact this building, for example? So in conclusion, in some cases, heritage infrastructure may survive the new regime better than modern buildings, but according to Chris Wardle, analyzing and understanding the response of heritage buildings to severe events is not simple. And I agree with that. So in closing, I'd just like to say that I think there are going to be threats and opportunities for heritage infrastructure. You have to figure out which ones those are.
Thank you very much, Jim, and I would like to open the floor up for questions. You had some questions starting about snow loads, if you wanted to start with that.
Go. the question is really, on one hand, you have an extreme of precipitation falling. On the other hand, you're looking at, say, an overall
Nice summer
month.
day.
Are you getting a significant, do you have a lot more rainfall? You had a 200% increase in the extreme of the rainfall in July. But what would the overall rainfall be in July, or the increase in that? Is it just that you're getting it concentrated, or are you getting a lot more rain in July? Because that may not have so much of an effect on buildings per se, but it certainly on other things, recreation, farming, etc.
Right. The answers to your questions are all available in the report we did for in the GTHA. So you get all of the averages and number of days of this, number of days of that in there. In general terms, the modeling for this area suggests a 2 to 13% increase in precipitation, a 2 to 4 degree increase in average temperature. So that's probably good. It will be good for the farmers, it will overall, and it will be good for you and I because we can get outside in the sun more.
Except
Not
if the precipitation on an extreme wipes out a crop, then it's not so great.
Right, and that's why you need to look at extremes, and that's why we did the extreme study, because the extremes are the things that drive us. So one of the things that we're looking at now is how do you make farming resilient, or how do you make buildings resilient, for example. And you can do that in two ways. You can either design them stronger to meet those conditions, or you can design them to fail. So you say, okay, if this condition comes, I know it's going to fail this way, I can rebuild it in a week, or I can rebuild this structure in 2 weeks. So that's a lot of the way the design is going now, away from stronger is better to let's design it so that we know how it's going to fail, and then let's replace it. Does that answer your question? Yes, ma'am.
You had mentioned one thing that we could do is run a fine scale model of climate change. How do we do that, or do we get you to do that?
Yes, I can do it. There are a number of companies out there that can do that now. What you do is, okay, I have to step back a little bit. The way a weather model works is that you make observations about every 300 kilometers around the world. Those observations, both by balloons and on the surface, are then put into a model, and all of the forces are balanced to give you a snapshot of what the atmosphere looks like in 3 dimensions at that particular time. You then use that snapshot, put it into a model that has all the physics and chemistry and everything built into it, known as a weather model, and you let the model march forward based on the known equations of how weather unfolds. And then after 6 hours, you get another set of measurements, and you can check one against the other. So that's the way a weather model works. Every weather model in the world works out. You can run, what we did for the City of Toronto was basically use the same approach, only we drove it with a climate change model. So we took what the climate change model said for the 2040s on a particular day, and we ran the weather model every 6 hours and then matched it against the climate model. So what it did was it generated, based on the climate model output, a series of hourly weather situations, which we then did statistics on to figure out how the statistics in the future would change from the statistics now. And you can do that for any location anywhere in the world.
But would the study you did in Toronto, would it not be similar, give or take a bit, this way or that way?
No. Do you remember the figure I had up there that showed the distribution of snow across the city? You will not get that. What you get if you use a climate model is you'll get an average value for that whole 50 kilometer by 50 kilometer area. What I showed you there was a kilometer by kilometer distribution of snow, rather than just, okay, snow will be down by 20% overall. And it showed that it was a difference between a 60% reduction and a 200% reduction. Right? So again, it all depends what you want to do. If you're happy using a 50 by 50 kilometer average, go for it. If you want more detail about the stuff in your area, then do a fine scale study. That gives you more information.
Thank you, excellent presentation, James. And you mentioned the fire in Fort McMurray, but in your opinion, is it a probability or a possibility that that fire was caused by climate change?
I'm not going to commit myself one way or the other. Let's just put it this way. Our climate is changing. We're learning more and more about how climate changes. Was it very dry out there? Yes. Should there perhaps have been a bigger fire break around the town? Maybe. Well, probably yes. But the way forests rejuvenate themselves is to burn every once in a while. So probably in our history, there have been a number of forest fires. There was a forest fire in northern BC in the 50s, I believe, that was so intense that it actually turned the sky blue all around the world. So there was smoke in Europe from the fires in BC. Okay. Now, was that as big as the one we just seen in Fort McMurray, or as strong? I don't know. I have to look into that actually. Everything is probably caused by climate, but it all depends what you're asking. Are you saying, is mankind responsible for the fire in Fort McMurray? Probably not. We're not that grand. We can't control the weather. We can't control nature. Nature controls us, and that's just proof that it does. Sir?
Maybe I misunderstood what you were saying, but just before you ended, you said you have the alternative of designing to survive all conditions, or, as an alternative, design at some point to fail.
Correct.
I can understand the former, but the latter obviously would raise a whole host of life safety conditions.
Yes.
How do you rationalize that latter part?
Does that have anything to do with climate change and I don't know. Yes, there are all sorts of ethical questions involved there. But again, for example, if there was a high water that could knock a bridge off its moorings, long before the bridge was knocked off its moorings, the bridge would be closed. So in theory, there would be no risk to anybody being on the bridge. How it actually failed, whether it just fell over or cantilevered over or did something, again, that's a design issue. I'm not an expert in that area, so that's probably a question to ask an engineer, rather that designs bridges or designs something that failed. But you're right, there are ethical issues around it, and that we have to be careful. Sir?
I imagine your work is being communicated to the Ministry of Housing and the government bodies that change building codes and engineering guidelines.
Yes, they know about them.
They know about them. Is there any movement afoot? I'm a small building designer, so I design roofs and snow loads. I'm probably, the community probably will just always follow the building code. I guess a real diligent designer might say, well, we should call you and get a climate risk assessment done. How is that going to unfold? Is that going to, do you perhaps have a timeline? Are we going to see changes in the Ontario Building Code in the next few years that are going to mandate risk assessments for certain building classes?
I don't know what the timeline will be. I do know that they are looking at the building code and trying to make changes to it, but as in every government organization, there's a time delay from when they find out about something until they do something. So if you want to be safe and duly diligent, I would suggest you ask the question of a number of designers who take that into consideration and say, should I be changing my consideration? Because building code is basically, if you do it this way, things should be okay. But if the building code is changing or should change, then who's at risk? Who's liable? I mean, those are the kind of questions that are being asked right now. So I'm sorry, I'm sort of wandering around your question.
Well, yeah, your inference has a huge impact, obviously.
Yeah, it does, yes.
It's a very significant suggestion that our code and safety factors may not be adequate. That's a big concern.
So what I would do is reach out to, I think it's Engineers Canada, Philip Lapp, if you know him. He's looking into that very question.
Thank you.
The one at the back.
Sorry, so how's acid rain doing, by the way? Is it over? Finished, or is it increasing?
Well,
That affects our heritage
we've always
buildings.
had acid rain, and we'll always have acid rain, but in terms of protecting forests and stuff, most of the reductions that we understood when we first started have been taken care of. They're now ratcheting down the levels to about half of what we said they should be down to, because they found some sort of fine scale effects that they hadn't seen before. Problem is, over the last 10 years, we haven't done much research in that area, so we don't know exactly where we are.
I was also thinking more about the heritage buildings with acid.
Yes, so you will still get some, but it's far less than it was a few years ago. Yes.
The engineering and the present building code, as all building codes are, is already a risk assessment. You're only making predictions based on probability of something failing, and it's all based on, well, where's a safe cutoff at probability? We simply can't afford, and I think you were implying this in some of your statements without maybe saying it, we can't afford to build for every possibility.
No, we cannot.
You know, there could be an event that's going to make everything collapse. And if we say, we're going to build so that nothing will ever collapse in any event, we simply can't, we're paralyzed. Everything is an assessment and a risk assessment. And that's what the building code is based on.
Correct.
And it changes. In certain areas of Ontario, the snow loads went up in the late 70s after winter storms of 1977 and 78. And in the recent changes to the code, they're going down in certain areas. And so it changes all the time.
Right.
It isn't instant to change.
The difference with climate change is that in the past, we were able to take historical data and say, okay, based on history, or climbing or whatever, and it was sort of it was easy to project into the future. That's no longer the case. Climate change no longer gives you that luxury. So you can't take historical data and use it as a guide for the future. So you have to run something more sophisticated like a model because there are nonlinearities built in because of the things that we're doing. And so you may find that in some cases using a linear projection is going to be way worse than you need it to be. In other cases it won't be enough. So again, I think really what you need to do today is just to ask the question, how is climate change going to affect me? What is the best science? Base your decision on that, and that's all you can do. You're taking a risk, you're making a decision, but at least you've considered it, and that's what you need to do.
Yeah, and if I could just add another comment, that you were saying, well, maybe you shouldn't insulate, or there's some you could possibly not insulate older buildings so that you don't increase the snow load on them, but that's assuming that the older building is insufficient in the way it's constructed.
Correct.
I think you have to realize.
Some of them are better. Yeah.
You got to analyze the building first before you decide if it's suitable to do
Absolutely.
something. And insulation has other effects.
The message I got across was that it's not simple. That you have to look at many factors, and today you have to look at many more factors than you did in the past. Somebody had a question, yes.
In your opinion, due to climate change, do you suggest in the future our Great Lakes are going to increase or decrease in depth?
All the projections are that they will decrease.
Decrease, even though the last couple of years we've had major rainfalls, and actually in the Windsor or Essex County area, the actual water has gone up by quite a bit, where we've actually had flooding that we haven't had since the 70s.
Yes. Again, it's location specific, and how it actually plays out is a little bit uncertain. For example, why is it so dry in northern Alberta this year or over the last few years, whereas some other places are getting floods? And that's just a matter of balancing off all the forces in the atmosphere and water being taken away from certain areas and being dumped in other areas. So again, I don't think there's any clarity on that. Most of the models I've seen suggest that the Great Lakes will decrease, not increase.
I like this information that you get for these models, is that taken over a 10-year period, correct?
The ones that we did for Toronto were a 10-year period just because of the computer cost involved, but most of the decisions are made on 30-year averages.
On 30-year average.
Yeah.
Like, wouldn't you suggest there's more of a cycle than these 30-year averages? You know, for example, like I just said, we had a lot of flooding in our area in the 70s, and then we had a dry climate in the 80s where the temperatures increased, and now they seem to be going down, and we're getting more flooding again. How do you design your infrastructure and everything based on this if we're gonna have to change the way we design things every 10 years, every 20 years, based on what we think it's going to be now.
You can only do what the data suggests to you. There are historical data, there are model data. You're not going to make a judgment, unfortunately. Or somebody's going to have to make a judgment, and then and most people will just follow the building code. And for the most part, that will be okay. Yeah.
I represent ACO Muskoka, and in your 2005 event where there was a little spot over Toronto, we had the same event coming across Georgian Bay that hit us.
Yes.
And we've just experienced our second 100-year storm in the last 2-3 years.
Yes.
What's going to happen to the jet stream over this period of time as we go forward? Because it seems our weather is so dependent on where, the direction of the jet stream across Lake Huron.
The jet stream is going to become more wavy, so you're going to get more extremes. Colder some years and warmer others, more rain, less rain. So you're going to get, unfortunately, it's going to become more uncertain. I'm sorry, I'm not giving you the answer you want, but it's an answer that's hard to get. The jet stream will probably move north, but it will become much more elongated and with more waves in it. So because it's moving further north, you're going to get more cold air. It's also going to be more warm air up in the tongues that come up from the south. So the intersection of the hot and cold is going to be in a different place, and those intersections are really storms.
Province's playground.
Province's playground. Other questions? Yes, sir.
So it's a new discussion. Have you heard of any practical solutions to the forecast extreme weather in terms of heritage buildings, be they residential, commercial, churches, whatever, brick or frame? You're telling us this is what's coming, we have to react to that. Have you heard of how communities are thinking of reacting to this in terms of preserving their heritage buildings?
I'm sorry, I'm not in the heritage building area.
Yeah,
I've not heard of anything in particular that they have done other than not insulating roofs and trying to look at foundations to see if they can be strengthened or protected because they were built based on a certain set of ideas when they were put together. Some of them were good ideas, some of them were not.
more ant traps, obviously, if the insect infestation, but that seems
More ant
necessary.
traps, yes.
Sure.
May I also suggest that our the strategies of static design for structures now actually evolve a little more into more of a, instead of thinking of a building as a static structure, in fact, it's actually a dynamic structure as a response to climate change.
Yes.
Especially because climate change is getting more extreme.
Yes.
Any more questions?
Thank you very much.
That was excellent. Thank you. On behalf of the Marriage Conference, that's for you.
Thank you very much.
Treatment. Thank you very much. And thank you all.